So homogeneous linear equations with constant coefficients. So this section is the same thing we've been doing. For example, that for instance. And how we would solve for this is to get the characteristic polynomial, solve for the R value, and that's going to be our rules. Right? All we're doing is just expanding it to now higher orders, where we will, again, we have, degree of differential of 5, 6, 4, 3, anything on top of that. Again, all it's saying is we do the exact same process. First we do is find the characteristic polynomial or characteristic equation, find the zeros, and then from there we have our three situations. If they're distinct, therefore each individual answer or each individual solution will look like this. If they're complex, this is going to be a little different now. We're going to have two of them. One is cosine, one is sine, not the addition of them anymore. And repeated ones are going to look like, again, same thing, except for t, it's going to be simply x now, to that power. Okay. Now, when it comes to the multiplicity of n, so for example, if you have r plus 1 to the third power, that means we're going to have this portion, then it's x, and then x squared, and then finally x to the third power. So this power represents what this one was going to be. If we have it repeated, imaginary, this gets a little bit more complicated because you got to be careful how that's going to go. So again, if we have this situation, so first we just go back to up here and do the normal process of it, and then we will have our 3 and 4, which is just x in front of here, and that's what we have here. So this is our basic one, this is our second power, and third power. So we have two multiplicity, 1 and 2. Okay. So same thing we've been doing. Now again, just knowing how to factor more carefully. So this is going to be r to the third minus 2r squared minus 5r plus 6 equals 0. We can use the grouping method because it doesn't actually work. So go back to pre-cal or college algebra, discard those rules, sign, do all that fun stuff to break it down. But for now, I'll give you one actually works. So the easiest way to go by doing that is probably doing synthetic division, since you know one answer already works. So then this becomes r squared minus r minus 6 equals 0. And then this breaks down to 3 and 2. So we get r is equal to 1, positive 3, and negative 2. So we have three distinct roots. So according to our formula, because we have distinct roots, our answer is just going to be in this format. So our solution is going to be C1, I'll use this one for the first one, e to the Rx, so 1 times x is just x, plus C2, e to the 3x, and then finally plus C3, e to the negative 2x. So it's the same situation as did earlier, but now we just have in terms of x instead of t. That's kind of like the only difference we've done so far. But again, all of this shows it goes to higher powers now of differentiable instead of just second order. Okay. Okay, so same process. Again, one actually works again. So doing synthetic division one more time. we get r squared plus 2r plus 5 equals 0. And this ends up going in the realm of the imaginary. So using the quadratic formula, we actually get r is equal to negative 1 plus or minus 2i. Okay, so we have this situation happening now. So according to our rules, we have distinct slash complex. So for the distinct one, we'll have c1 e to the 1x power. And now for our imaginary complex roots, we're going to have two of them. So first case is going to be e raised to the a power. Now again, according to this process, this is going to be a and this is going to be b. So to the negative x power times cosine of bx. And the other one is exactly the same, but we use sine instead. And now we just put this together. All right, let's keep going. So like I said, now we're going to higher orders. So this is 4, 3, 2, 1, 0. So this one's a bit of a pain to do so. R is equal to 1 actually works again. And when you do synthetic division, you actually get this back. Which again doesn't factor nicely, but the nice thing about repeated ones, you can repeat it itself, so this actually gets another repeated root of 1. And again, doing synthetic division one more time here, we finally get a nice quadrilateral. And then just breaking this down gives you r plus 2 and 1. So we have our four answers of r equaling negative 2 and 3 sets r equals 1. All right, so this is a combination again of distinct and repeated. So again, for the distinct one, but for the repeated one, we're going to have all the way to the n minus 1 power. So here we have m equaling 3, so we're going to have two of them. So we're going to have 3 sets, so y2, y3, and y4. So for the first one is just itself, so e to the 1x power. And for the second situation, we're just going to have an x in front. And for the last situation, it's going to just be x squared to the front. So you can think of it, so if m equals 3, it goes down to 2. So you can say 0, 1, 2. That's easier to understand. Because this is the same thing as saying e to the 0, like that, when it comes to repeated ones. And then finally, just put everything together. All right. Another one that's not so fun to actually factor. And this is actually a quite hard one to factor. There's no real technical rules that go about doing it. But it does factor kind of nicely, believe it or not. This ends up factoring to a polynomial times itself. Like that. And breaking this down using the quadratic formula gives us r is equal to that. So technically, this is an improper way of writing this, but it's easier to understand what we're about to do. This is basically the same thing as I just split them up. So you get two factors of each individual case. So this has multiplicity of 2 now. Now, because we have multiplicity of 2 now, we're going to follow the last situation, which is going to be this case here. Okay. So we follow the same process as the repeated one, as we did here, but now we're just going to have sine and cosine. So first we'll just write it as if it's not repeated. So this is going to be our A, this is going to be our B. So we'll have y1 equal e to the ax cosine of bx, which is going to be that. And then y2 is the same, but it's sine. So that's the non-repeated version. Now as the repeated version is because m is 2 and 2 minus 1 is 1, we just have one extra one here. So it's the exact same process, but we just attach x now. So very similar to just the repeated one above. Just like that. And then finally putting everything together.